So every day we've been introducing a new phrase that still describes the same thing, the same idea. Okay, we started with the slope of a curve, and then we moved into the word derivative on the second day, which was Leibniz's idea, which he got from the Latin. Then we moved into instantaneous rate of change, which was Newton's idea, and how you could use the derivative to do physics. And today we're going to talk about tangent. And tangent is another same thing. It's another phrase that is using the exact same math. So we're doing the same math for 5 days in a row. And every day it's just a different way to describe it. So we're going to talk about what we learned before, which was slope of a curve. And now we're going to relate that to what that means for tangent. And we'll also talk about a vocab word called nominal. We'll introduce what that, review what that means. Okay. Okay, so just to set the stage here, the slope of a line versus the slope of a curve. All right, the slope of a line. So draw yourself a random line. That slope has a point A, it has a point B. Remember, it doesn't matter how far apart those are on a line. They can be really close, they can be far away. It doesn't matter because the slope is going to be f of B minus f of A over B minus A. And this is our line. So that was day one when we did that. We also called that the average rate of change. Slope on a curve. Okay, now make something curvy. And the thing about a curve is that the points can't be so far apart. You can't have an A and a B super far. That B I'm going to cross out. It's way too far away. To do the slope of a curve, the A and the B have to be so close together that they're practically on top of each other. And so we use the same formula, but we throw limit in front of it as B approaches A, which is shrinking the gap between those two. So that's setting the stage for what we have been working on. Okay, this was, the Leibniz was the first guy, and he was the first guy to work on this idea of bringing the points together. Okay, Newton, same thing. He just called his H instead of B. Here's Newton's. Same thing, okay? His was just H instead of B. Same thing, the H is just very, very, very small. Okay, so on your curve for him, you'd have your first point, he called it X, and your second point was super close to it, and that was X plus H. And then he just made H be very small. Okay, so that was review, what we've done this week. So I want to side by side do the two different methods, and I want to you guys now to kind of make your determination of who you prefer more. Find the derivative of this parabola using either guy's method. So let's do Leibniz first. And we're going to do it, notice I didn't tell you what point we're going to do it in. We're going to do it at any point. All right, so what variable have we been using when we talk about any point? X and A, right? Okay, that represents any point here. Okay, so Leibniz would say df dx. And Leibniz would say that we're going to do the limit of f of x minus f of A over x minus A. Okay, that would represent any point possible. So A is your starting point, and then x could be anything on there. And so x would approach A. So that's how we'd get that set up. All right, so f of x is the original function, x squared minus 1. I usually put that in parentheses. And then minus the same function with a in it, so a squared minus 1. All over x minus a. And you might remember what's going to start to happen here. We're going to end up distributing the subtraction. And what happens is we end up with x squared minus 1 minus a squared plus 1. So do you see what's going to happen? Yeah, what cancels?
1.
Okay, the 1's cancel. And what are we left with?
X plus 1.
Yeah, we're left with the difference of squares. We are left with x squared minus a squared, and x squared minus a squared is difference of squares. So Leibniz always ends up with that kind of thing. An x minus a times an x plus a over the x minus a. So Leibniz always usually ends up with some kind of difference of squares, which is going to reduce away, leaving me with just one parenthesis of x plus a. Newton always ends up with the front term canceling out the back term, and then the h's reducing, but Leibniz always ended up with this way. Then we plug in any value, a, so this becomes, instead of x plus a, it'll be a plus a, and 2a. So Leibniz tells, we end up going, okay, the slope anywhere on this function will be 2 times a. So if anywhere is 7, the slope will be 14. If anywhere was -3, the slope would be -6. It's always 2a. So let's see how Newton comes up with the exact same thing. I'm just going to confirm it with you. So for Newton, we would do f prime of x. And his would be set up with the x plus h. So limit as h approaches 0. We would set his up at a plus h minus f of a. So that represents any point over h. Not a specific point, but any point. And so for Newton's, we would end up with a plus h quantities squared minus 1 minus a squared, just plain a squared, plus 1. And then we FOIL. We get a squared plus 2ah minus 1 minus a squared plus 1. And what always happens in Newton is things start to cancel away. The a squared cancels out with the other a squared. The minus 1 cancels out with the plus 1. We have 2a h over h. 2ah is all that was left over h. Those h's reduce, leaving me with nothing but 2a. So I get the exact same thing. So it's going to be your personal preference of which method you tended to favor and think was easier for you. But both guys worked out the exact same way. Okay, any questions so far? I feel like I'm supposed to be a summary for the week. Okay, so now let's talk about these new things. A tangent line. A tangent line is a straight line that skims off the curve at one point, but keeps its direction. So for example, if I drew a tangent line, I would skim off my curve right here. Okay, that's the direction of a tangent line. You can do it off of any side. So maybe the parabola might have a tangent line that skims off the curve and just comes down like that. That could be the tangent line. So anywhere I tell you to put a tangent line, okay, aim for this point and draw the tangent line. Or aim for, so on the parabola, if I told you to aim for right here, what would that look like? So I'd aim for your tangent point right there. What do you think? What kind of slope does it have right there? Well, let's back up. What kind of slope does this equation have? I just mean like direction. What kind of slope? Has positive slope because it's going in what direction? Going up. Okay? All right, and what kind of slope does this one have? Negative slope because it's going down. So if I told you to aim for this point right here, what kind of slope does that have? Zero. Has no slope. It's completely flat. It would come across and just skim across it and head like that. It's going to have 0 slope. If I told you to aim for this point right here, what kind of slope would you have? You should have positive because you're going to skim off and then go in that direction. Okay, you're following the curve and the way it's going right there. Those are called tangent lines. So every line needs a point and a slope. So the slope needs to be positive or the slope needs to be negative, but every line needs a point and a slope. And when we know that, okay, the point is always x1, y1, and the slope is always m. That's what we've been using throughout your math history. And when we write a line, the equation is y minus y1 equals m times x minus x1. That's called the point-slope equation of a line because it uses a point and it uses a slope to form an equation. That's why we call it the point-slope line. Every tangent line in calculus needs a point and a derivative. Because in calculus, the word derivative means slope. It's the same thing. And so we'll be using the point xy, and the derivative will be doing f prime. And so our equations will look like y minus y1 equals f prime of x times x minus x1. But it's the same. The derivative means the slope. So when I say tangent line, you got to come up with the point that you're skimming off of and the slope that you're hitting it with. So every time, okay, tangent line, I need a point and a slope. I need a point and a slope. Or I need a point and a derivative. That would be the same thing. So let's try that here. Okay, for this parabola, write the tangent line at 1. Okay, well I can estimate, here's 0. I can estimate 1 is about right here. So if I was going to draw the tangent line, I would draw it, and I think it's probably going to look kind of like that. But I need to know what's the point that it's hitting and what slope is it hitting with. The point it's going to hit at is x1, y1. So it's 1 comma, and I got to figure out what the y1 is. How do I figure out the y1 value? How do I know where it's hitting on that curve? How do you find the y coordinate? Just plug the 1 in. Into what? Into the equation. And what do we get? 3. Okay, so there's my point. My point I'm skimming off of is 1 comma 3. Now I need to find my slope, which is also known as my derivative. And to find that, you are allowed to use either Newton or Leibniz, whichever one you like. It is totally up to you. And I'm going to fast forward and pretend like we've already done that. I'm going to tell you that the answer turns out to be 2a. So at this particular point, at the point 1, 3, and I know that the slope is 2a, which 2 times anywhere, that'll be 2 times 1, because that's the x value that I'm working at. So the slope, or the derivative, will be 2. So I write the tangent line now. So my tangent line is going to be y minus y1 of 3, the derivative value of 2, and x minus 1. That's the end of your tangent line. You don't have to distribute. You don't have to get y by itself. You just stop and you say, that's my tangent line right there. That's the equation of the line that skims off that point. If you want to check your answer, I would recommend using your graphing calculator. I'd recommend graphing the parabola in y1 and your answer in y2 and look at it and see if it looks like it's skimming off. If it hits more than once, if it hits twice, then you missed it. You did not find the tangent line. Tangent line's only allowed to hit once. Okay, a normal line. Go ahead and pick a point and draw the tangent line. So the tangent line will skim off of it like that. The tangent line has to go up, just like the graph goes up. Okay, this one is the tangent line. Okay, the word normal is not the opposite of crazy. In math, the word normal means perpendicular. So I feel like you're learning so many words that just mean the same thing as something that you already know. You learned the word derivative, which already meant slope. You learned the word normal, which means perpendicular. So draw a perpendicular line. And perpendicular lines have to form what angles between them? 90 degrees. Okay, so do your best to draw something that forms a 90-degree angle. Okay, that is called a normal line. So first you have to know the tangent line, and then you can find the normal line. They both go through the same point. Okay, they have the point in common. So they share the point x1, y1. They both share that. The difference is their slopes. And do you remember how perpendicular slopes work? We reviewed that back first maybe week of school. How do perpendicular slopes work? If I tell you that the slope of something is up 2 over 3, do you know what the perpendicular slope would be? Okay, it's the negative and it's the reciprocal. Okay, so if the tangent slope is c over d, then the normal slope is always negative d over c. Okay, we call those the opposite reciprocals. All right, so if every line needs a point and a slope, every normal line also needs a point, but it needs a perpendicular slope. So instead of a regular slope, it needs a perpendicular slope. So we're going to try this again. Find the slope of this curve, and then we're going to do the normal slope of this curve. All right, to find the regular slope, you need Leibniz or Newton. It is up to you. So this time I'm going to do Leibniz, so dy dx, and that announces to everybody that I'm ready to do Leibniz. So x approaches a. So that would be 1 over x minus 1 over a over x minus a. So that's how I set that up. And I work my happy way through this derivative, getting the common denominators and stuff. And let's pretend we've done all that work. We get negative 1 on the top. We get a squared on the bottom. Okay, almost done. We call this the tangent slope. All right, what would the normal slope be? Positive, right? A squared over 1. So if that was the tangent slope, then we know what the normal slope is going to be positive a squared over 1. Okay, that's the only difference. The point is the same. The slopes are connected, but they are reciprocals of each other.